Okay, so I guess I have to introduce the speaker. Okay, so thank you for this opportunity. Okay, so the first talk of the day is given by Anna Jaskiewicz. I hope I pronounced the surname correctly. And the title is Constraint Discount Stochastic Games. Please, Anna, the stage is yours.
Okay, thank you very much. So first of all, I would like to thank the organizer for the invitation for this workshop. And my talk seems to be different than the other talks given at this workshop. Namely, it will concern stochastic games in discrete time with discounted payoff criteria. And unfortunately, I am not going to appeal to mean field games, mean field approach. But anyway, this talk is based on my recent joint paper with Andrzej Nowak, exactly on constrained stochastic games. And the plan of this talk is very simple. I have not written here, I just say very quickly. So first of all, I start with the model of a stochastic game with countable state space. And I want to mention some papers on stochastic games without constraints, and then I go to the results for the games with constraints. And finally, I will present some results for games with uncountable state space, with general state space. And first I will do this for games without constraints, and then I mention recent results for games with constraints. So this is the plan of my talk. So first I start with the model. The model of a stochastic games is as follows. So we have the set of players. This is for finite set from 1 to n, and of course, since this is a game is greater or equal than 2. We have a countable state space, so it could be finite or infinite. AI is the action set for player I. It can depend on the current state, X. By capital A, we denote the set of action profiles. And each player has its own cost function. I will speak here about cost instead of payoffs rewards, so that each player has its own cost function, CI, that depends on the current state and the action chosen by the action profile chosen by the players. And the cost function is bounded for each player. And we have the transition probability of the next state, X prime, given the current state and the action profile A of the players. Since we will deal with discounted cost criteria, so alpha denotes the discount factor for each player. The evolution of a stochastic games is as follows. So there is an initial state x1, which can be given or it can be chosen randomly with some given initial distribution, but at the moment assume that x1 is given. And the players choose simultaneously choose their actions, and we have a profile of actions A1, and immediately they have to pay their costs. In period 2, the process moves to the next state, x2, according to this transition probability, and the situation repeats. In this way, we obtain a history of the process up to the TIF period if the game ends in period T or is in period T, then we have the history of the process that includes the up to the state T and all actions profiles chosen by the players in the previous states. And we have strategies for the players. I will consider two classes of strategies. The first class is this class of general strategies. A strategy for player I is denoted by pi I. It's a sequence pi it, where each pi it is the conditional probability given the history of the process up to the state t. The conditional probability on the action set of player I. And the set of all strategies for player I will be denoted by capital pi I. And in particular, we will be interested in the set, in the class of so-called stationary strategies. So first we define the set phi I is the set of all transition probabilities phi I from X, from the state space to the action set AI. And the stationary strategy, sometimes it is called Markov stationary strategy for player I, is a sequence phi it, where each phi it equals some constant element from the set phi I. So in other words, it's a constant sequence. And that's why I will identify this sequence, it's its element phi I. And that with a little abuse of the notation by capital phi I will denote also the class of all stationary strategies for player I. So in other words, stationary strategy for player I depends only on the current state of the process, does not depend on the history, does not depend on the period of the game. And as I mentioned, I will consider discounted costs for players. So if I have initial state X and the actions and this strategy profile pi chosen by the players, then I define the expected discounted cost for each player. For player I, in the infinite time horizon, for player I, it's defined in the following way. So alpha is the discount factor, and this I multiplied this by 1 minus alpha just to normalize this cost. This guy is well defined since CI is bounded, the cost function is bounded for every player, and E is the expectation operator, EX pi is the expectation operator with respect to the unique probability measure, PX pi, defined on the space of all infinite history of the game, according to the Ionescu-Tulcza theorem. This probability measure is, of course, induced by the transition probability, P, the initial state X, and the strategies chosen by the players. So from pi 1 to pi n. And this is the Nash equilibrium theorem, which is probably well known, but just for convenience, I wrote here. A profile pi star is a Nash equilibrium if this inequality holds for every player I and every initial state X. So neither player can deviate unilaterally from the prescribed strategy. So if player I decides to deviate from this, from the equilibrium strategy, then he cannot get less in this case. And the stationary Nash equilibrium is a Nash equilibrium that belongs to the class of stationary strategy profiles. And now we have the first theorem that every discounted stochastic game possesses a stationary Nash equilibrium, which means there exists a profile of stationary strategies phi star such that the inequality, this inequality holds for every initial state X, for every player I, and every strategy pi I of player I. And of course, here I do not mention an assumption in this theorem, in this statement, but I will do it if I will say something about the papers on that the theorem, in which the theorem was proved. So first of all, I would like to say about two papers published in the same year, in 1964, namely Fink and Takahashi, proved independently that non-zero sum stochastic game with finite state and with finite action sets possesses, they proved that such a game possesses a Nash equilibrium. And why that was not difficult to prove, because first of all, they noted that the class of stationary strategies phi can be viewed as a compact convex set in some Euclidean space. This is true because the action sets are finite and the state space is also finite. Then they wrote the Bellman equation for each player, and then thanks to that they could define the best response mapping, and so-called the Nash correspondence, and then use the Kakutani fixed point theorem, and they obtained the Nash equilibrium in the set of stationary strategies. In order to show that this is indeed Nash equilibrium in the set of all strategies of the players, they use dynamic programming principle for each Bellman equation written for each player. So that is the proof of this theorem. And these works generalize the first paper on stochastic games published by Shapley. Namely, Shapley considered zero-sum stochastic games with finite state and action sets. And exactly, that's the year of publication of this paper is just the beginning of a stochastic games. And now the next paper, which I want to mention, is the paper published by Avi Federgruen in Advances Applied Probability. And he also proved this theorem that every stochastic games possesses Nash equilibrium, but this was done for games with countable state space. I mean that infinite state space and compact metric action spaces. So since A is AI, each action set of player I is compact metric space, so he needed some extra assumptions, continuity assumptions, so that the transition probability and the cost functions are continuous on the action sets of the players A. And second thing he introduced the topology of pot-wide convergence in the set of stationary strategies of the players. So we say that the stationary strategy profile converges, phi n converges to some profile phi 0 in phi. Phi it's like here, it's phi, it's a product, it's a product set of stationary sets of stationary strategy sets of the players. If and only if for each component we have weak convergence of such a probability measure. So phi n given x converges weakly to the phi 0 given x in the probability measures on the action set for player I. And then he showed that the expected payoffs are continuous. And he noticed that the set of stationary strategy profiles can be seen as a convex compact subset of a locally convex topological Hauser space. In other words, he identified the set of stationary strategies for player I with such an infinite product of the set of probability measures on the action space of player I. And then again, he wrote the Bellman equation for each player I. Thanks to that, he was able to define the best response mapping, the Nash correspondence, and then he used the generalization of a Kakutani fixed point theorem given by Klicksberg and Fan. And then again, the dynamic principle helped to prove that this stationary profile of strategies is indeed an equilibrium in the set of all strategies of the players. And this is all on games. That's the main results for games with countable state space. And now let us go to the model of a constrained stochastic game, also with countable state space. So we have the model similar to the model considered by Feder-Gruen. So we have AI is the compact metric action space for player I. It also can depend on X, but I just skip here for convenience not to write X. We have CI0. This is the cost function for player I. This cost function plays the same role as CI in the previous model. And we have extra functions called constraint functions for player I. These functions are CIL. And we have constants kappa IL. And these functions, constraint functions and constants, help the player to design additional constraints. And at this time, we have the initial distribution eta, so that's the distribution of the initial state. And as was done earlier, for any profile of strategies of the players, we define the expected discounted costs. And these costs are defined for the cost function, so-called the objective function of player I, as well for the constraint functions. And the problem of player I is to minimize his expected discounted cost connected with this function CI0, subject to the following constraints. So he wishes to find strategy that minimizes his expected cost, but at the same time, he wishes the constraints. He wishes the constraints to be satisfied as well. And all strategies that satisfy these constraints are called feasible strategies, and the set of feasible strategies for player I against the profile of other players, pi minus I, is denoted by the delta I of pi minus I. So that's the strategies that satisfy these constraints, that are feasible strategies. And the Nash equilibrium in such a model, in such a constrained stochastic game, is a profile pi star, such that each pi I star is feasible strategy, and each pi I star minimizes the objective cost for player I, and this must hold for all players. And due to the additional constraints, the system of Bellman equations and the techniques from dynamic programming do not work in this framework. So we cannot use Bellman equation, write them, and just somehow to get the solution. No. Here does not work because the presence of constraints. So idea is to use the occupation measures. And what we do, we start with so-called correlated strategy. A correlated strategy pi t is a sequence pi t where each pi t is a conditional probability on the action on the product of the action set of the players, given the history of the process up to the TIF period. So in other words, all players act as a one decision maker, so we can say. So we have just an MDP model, and in this case, so we have one decision maker, so we can say. And mu is called an occupation measure if it's defined in the following way. So mu of k is a subset of x of the product of state space and the action set of the players, and we define such a measure mu. It is called occupation measure, and it's not difficult to see that mu is also a probability measure on the action set, on the product of state space and the action set. And here I have some comments. So first comment is that every profile of strategies for the players defines, of course, a correlated strategy. The second remark is that not every mu, which is a probability measure on the product of state space and the action sets of the players, is an occupation measure. Only those measures which satisfy the following equation. This equation exactly follows from the definition of the occupation measure. It's not difficult to prove that if mu is defined in this way, then it must satisfy this equation. And mu hat is a projection of mu on x. And having defined mu, occupation measure, we can express the expected cost for the objective function and for the constraint functions for the players with the aid of occupation measure. This follows again from the definition. So instead of writing the expected cost with the aid of expectation and pi, so we can write this with the aid of occupation measure mu. And now what we do here. So first of all, we consider the set of all occupation measures. This is calligraphic M. And remember that this set is induced by all correlated strategies for the players. And this set is convex compact subset in the set of probability measures on state space and the action set, when this set of probability measures is equipped with the topology of weak convergence. This result was proved by Borkar in 1988. And then, having M, calligraphic M, we define the set Mi, the set of probability measures on the product of state space and the action set of player I, defined as follows. So mu I belongs to the set if there exists a probability measure mu such that mu I is the projection of mu on the action set of player I for every x, of course. And thanks to that, we can claim that Mi is also convex compact subset in this set of probability measures on the action set and the action and on the action set of player I and the state space X. And then our optimization problem for player I expressed here can be written with the aid of occupation measures as follows. So if phi is a profile of stationary strategies for player, it's a profile of stationary strategies, and mu I is an occupation measure in MDP, in such an MDP. So player I is a decision maker, and the other players play phi minus I. So that's the strategies, stationary strategies from the profile. So that the objective of the goal of the player I is to minimize his cost subject to the following constraints, and subject to mu I is a probability measure on the state space and the action set of player I, and subject to mu I is occupation measure. So that this equation says that mu I is indeed an occupation measure. And we know from the papers that the mu I that satisfy this problem, this set of mu I satisfying this problem is non-empty, convex, and compact subset of calligraphic Mi. I denote this set of solutions by a calligraphic OI of phi minus I. And now the solution is as follows. So first, we assume that the initial distribution is such that each state is chosen with positive probability, and we define the correspondence S from the set product set of Mi into the same set as follows. So in other words, we take some occupations measures, mu I, mu1 to mu n, and then thanks to this integration of this measure, we obtain the stochastic kernel phi I. This is a stationary strategy for player I. And what is important, that this strategy phi I is unique. It is unique thanks to our assumption that eta x is positive for every x. So that's why we have here uniqueness. And then having phi I, we define this with the aid of this integration, we define this correspondence. What is important, that S is non-empty, ampere semi-continuous with compact values and also with convex values. Then we can use the generalization of the Kakutani theorem, and we obtain a fixed point mu1 star up to mu n star. And again, using this integration, we obtain the stochastic kernels phi I star. So we obtain the stationary strategy for each player. And these stationary strategies obtained through this integration form a Nash equilibrium in constrained stochastic game. this is the main idea. The idea is first to use correlated strategy. Thanks to that, we have a compact convex set in the set of probability measures on the state space and action sets. And then working in this set of calligraphic M, we can obtain a Nash equilibrium. So the main theorem is as follows: assume that since we deal with compact action sets, so again we need some continuity assumption. So P is transition probability, and the constraint and objective functions are continuous on the action set, and there exists a function W such that CIL, each function CIL is the absolute value is bounded by the function W. This assumption is needed because we want to take into account unbounded cost functions. So W can be unbounded. So in this way, we can deal with unbounded case. And of course, we need some extra integrability conditions of discounted costs, which I don't want to write here. So there are some integrability conditions, plus of course the Slater condition as well, which is needed here. And then having assumed this assumption, we have the constraint. We have the following theorem that every constrained discounted stochastic game possesses a stationary Nash equilibrium. And so I only mentioned that the solution for the arbitrary initial distribution and unbounded cost and constraint functions are obtained via an approximation of gains with truncated cost and constraint functions and disturbed initial distribution. So the idea is first to consider such a positive initial distribution and bounded cost functions. Then, thanks to this correspondence, as we obtain Nash equilibrium for such a specific game, and then we take we truncate the cost function and take a disturbed initial distribution, and then we take the limit of such equilibria. And it turns out that this is a Nash equilibrium in the original game with unbounded cost and every initial distribution, an initial distribution. And there are some predecessors of our paper, of our results. So first of all, I would like to mention the paper of Altman Schwartz, who were first to consider the games, constrained stochastic games with finite state and action spaces. So they need not to consider the set of calligraphic MI because the action and the state space, the sets were finite, so that the probability sets of the product of state space and the action sets for player I were compact. So that was not a problem. The second paper, and that is paper due to Alvarez Mena and Hernandez Lerma, who considered countable infinite state space model with compact metric action spaces. And again, in this case, since X is infinite state space, they couldn't use the set of probability measures on the product of state space and the action set for player I, because this set is not compact in the weak topology. So their idea was the following: to use some approximation of the original game by games with finite state spaces, but they have to pay an extra cost, so they had to assume additional assumption, and this assumption is expressed in terms of transition probability. So that's not every Markov model satisfies this this assumption. And now let me move to the games with uncountable state space. First, I would like to say something on games with without constraints. So I mentioned the last result that was proved by Feder Gruen. So he showed the existence of a Nash equilibrium for games with countable infinite state space models. And there was a question about the existence of stationary Nash equilibrium for games with general state space. And the problem of the existence was not had been unsolved till 2015. So from 1978 to 2015. In this year, 2015, Levy and McLennan gave a counterexample, and they showed that in general, discounted stochastic game, the stationary equilibrium need not exist. The counterexample is quite complicated, so they needed 8 players to construct such example. However, the state space is very simple because it's interval 0, 1. The action sets are finite. The transition law is a convex combination of a probability measure depending on the current state. It's a uniform distribution on x on the interval x1, and the Dirac measure concentrated at point 1. However, the coefficients in this convex combination are quite complicated, so I am not going to write here them. Also, the payoff functions are complex. And Levy and McLennan took advantage of, in order to show that the equilibrium in stationary strategies may not exist, they took advantage of the paper by Kolbeck and Mertens on strategic stability of equilibria. So for many years, the problem was not solved. So that's this is also interesting that that stochastic games are not so easy to consideration, general stochastic games. So that's it was so his counterexample confirmed that we cannot expect stationary equilibria in general stochastic games. And now, why the problem is so difficult in this case? The problem of the existence of stationary Nash equilibrium, of course, is a problem of a fixed point in appropriate function space. So first of all, we have a problem of the sequential compactness of the set of stationary strategies for player I, if X, the state space is uncountable. Then the second problem is connected with the continuity of the expected payoffs on the product space of stationary strategies. So there are two remedies, two theorems which can be used to get the compactness. The first one is to introduce the weak start topology in the set of stationary strategies, and the Banach-Arago theorem gives the compactness of phi I. However, in this case, we lose continuity of the expected payoffs. And the counterexample was given many years ago by Elliott, Carlton, Marcus in the paper published in SICON. The other remedy comes from the Arcela-Ascoli theorem. And the idea is to use the topology of uniform convergence in the set of stationary strategies for some specific games. Then we know that the family is compact, it's uniformly bounded, and the quick continues. However, And the problem with such a games is often that, for instance, when we, let's say, consider Lipschitz continuous functions with constant 1, Lipschitz constant 1, then it may turn out that the best response of other players is it can be Lipschitz continuous function, but with constant 2, and so on. This constant, the sequence of constants are growing, and we cannot pack it in one ball. So it's also maybe for very specific games we can use this this theorem, but generally it's difficult. There are problems here. So what kind of results we have for games with general state space? The first result which I want to mention is due to Barelli and Dagan. They consider transition law, transition probability P, and they assume that it is absolutely continuous with respect to some non-atomic measure mu. And they obtain the equilibrium strategies that are independent of the stage of decay, that are independent of the stage of the game, so that they are stationary in some sense, but they may depend on the current state, the previous state, and the action profile chosen by the players in the previous state. So in stationary, just in the usual stationary, when we consider a stationary strategy, so that the strategy depends on the current state. Here we have dependence on the current state, the previous state, and the action profile chosen by the players in the previous state. If we add extra assumptions, so if we assume that P is a convex combination of the stochastic kernels that may depend on the current state with coefficient gk in this convex combination, which are Kara-Teodori functions, then we can get rid of the dependence on the action profile chosen by the players in the previous state. So in this case, we can obtain the equilibrium strategies that depend on the current state and the previous state. And that's why we call them almost stationary Markov strategies, almost stationary Markov, almost stationary because they may also depend on the previous state. And what is important that within our framework in this setup, we cannot expect more, because the counterexample given by Levy and McLennan belongs to the games considered here. So that's as I mentioned, P is the transition probability is a convex combination of some measures, and Q, and that is also important that Q is absolutely continuous with respect to non-atomic measure mu. And both papers look for a fixed point in the set of Nash equilibrium payoffs. So not in the set of strategies, but in the set of Nash equilibrium payoffs. And both papers make use of the Mertens theorem on measurable choice of some function. So that's also important tool in this theorem, in these two results. The other papers in which the equilibrium is proved, it belongs to Mertens and Partasarati. They proved that the existence of subgame perfect equilibrium in such a general stochastic games, and in this equilibrium the entire history of the game counts so it's included. And now a few words about constrained stochastic games with a general state space. So first of all, I want to say that the Levy and McLennan example implies that the stationary Nash equilibrium in constrained stochastic game need not exist. That also follows from their example. But we have one paper this is the recent result of François Dufault and Thomas Prieto-Rimont, and they proved the existence of a stationary Nash equilibria for so-called Arad constrained stochastic games. What is the Arad? Arad means additive reward and additive transitions, which means the following, that the cost and objective function for the constraint and objective functions for each player is as follows. And again, this is two-person game. It's as follows. So CIX A1, A2 has such an additive structure. And also the transition probability have such an additive structure. So P can be expressed in the following way with Q1 and Q with two measurable function Q1, Q2. Assuming these two conditions, they proved the existence of a stationary Markov equilibrium. And our recent result also is connected with, is also done for games with general state space. But what we have here? So first of all, we assume that the transition probability is absolutely continuous with respect to some measure mu or lambda. Of course, we need some continuity assumptions, and we do not assume that the action set is dependent on X. So we assume that AI is independent of the current state X. And then we can approximate the original game by games with countable state space, and in this way we obtain stationary epsilon equilibrium, and then we take the limit of such equilibria when epsilon goes to 0, and we get a result on the existence of so-called weak correlated equilibrium. And this is correlation mechanism introduced by Moulin and Vial in the paper from 1978. So idea is as follows: if all players, but players accept to use a correlated strategy to select an action profile in each state, and player I decides to play independently of all of them by choosing a feasible strategy, then the action profile of players J different than I is selected with the marginal probability distribution of the correlated strategy on and A minus I. So weak correlated equilibrium means that no unilateral deviation is profitable. So in other words, each player before knowing the outcome of lottery must decide whether he will play according to the outcome of the lottery and commit himself to play this strategy, or no, he said, no, I'm going to play my mixed own strategy. And in weak equilibrium, such a unilateral deviation does not pay off. And we have such a result on the existence of weak correlated equilibrium in the class of constrained stochastic games with general state space. As I mentioned, we cannot expect more we cannot expect more because on the Levin and McLennan counterexample. Okay, and this is all. Thank you very much for watching.
Okay, thank you very much for your talk. I think we have time for a couple of questions from the audience, and if anyone attending online has also a question, I think he or she can write it in the chat box.